Okay, and you know what? We are in a world where you know there have been advancement in technology, and because of that, software have actually been developed to handle model complexity. Okay, so we got a software like R, we got a Python, we got a MATLAB, we got a Starter, we got, there's different kind of software that are available for grab. Okay, so F-test is a special case of partial F-test. I just wanted to know. F-test is a special case of partial F-test, and I'm going to tell you why. When you are comparing model with intersect model, we use F-test. I'm going to say that again. When you are comparing a model with an intersect model, okay, you know what I mean by intersect model? In an intersect model, we don't have any predictor, okay, and what we normally use is F-test. But you know what? When we are comparing between uh, models that have one or more predictors, okay? When we are comparing between models that have one or more predictors, but only that the difference between them is just by regressor, then we're actually going to be using partial F-test, okay? Therefore, F-test is a special case of a partial F-test, okay? So, and that was why I said when you have a simple model where you are regressing y on 1, this is more or less like an intersect model. There is no predictor in this model, okay? When you are comparing this, okay, with a model with a predictor, actually, you're actually going to be using F-test. But in a situation where you are comparing between nested models, where at least one of the model have a predictor in it, of course, you're going to use what we call a partial F-test. Okay, you're going to use what we call a partial F-test. Okay. Now, is there anyone who want to ask question before I move to another topic? Is there anyone? Or is there anyone who have a trouble time distinguishing between the partial F-test and the F-test? Is there anyone who need more clarification? Okay, are you guys hearing me?
Yes.
Okay, so okay, I'm gonna read my chat right now. Somebody said, so the F-test is to test a model, the partial F-test compare two models. Okay, you know, maybe I'm going to say the F-test is a test for the overall significance in the model, the overall significance of the parameters in the model. So if you put it that way, I think I'm actually going to be fine. Okay, so F-test is to test for the overall significance of the parameters in the model, while the partial F-test compare two models. But you know what? When you say two models, at least one of the model must have one predictor. Have I answered your question now? Okay. Yeah, somebody say yes, thank you. Okay, so that is going to be the end of the lecture today for the partial F-test and the F-test. I think by now, you guys will actually appreciate the difference between the partial F-test and the F-test when you are fixing linear regression model. Okay. Yeah, I want to welcome you to another topic. Can you guys see the model selection right now?
Yes.
Okay, so I want to welcome you to another topic. And you know what? This particular topic is very, very important. Okay, and it is called model selection. Okay, uh, some of you will argue with me that can we say partial F test is one of the two in model selection? Then I'm going to say yes, because the use of partial F test will actually enable you to compare two models, only two models. Okay, you cannot go beyond. You can't use partial F test for more than two models. And at times in research, we may have more than two competing models. Okay, so you can only use a partial F test when you have two models. And you know what? When not only two models, they have to be nested. Okay, but what if in the situation where maybe they are not, whether they are nested or not, or they are more than two models? Okay, so can we have an extensive kind of explanation for model selection? And that's exactly what we want to do now. And let me tell you something. We're in a world, okay, where we actually want to have control over our society. We want to have control over the world around us, and most of the time, we normally have more than one model that we want to fit, and we're going to be looking for a way. Okay, what criteria am I going to use in be able to conclude on the best model? Okay, there are models. Okay, and then one of the models is actually going to be the best, because we are actually want to take decision using the best model, and that's exactly what we want to do in this topic. Okay, so like I said, the goal, what is the goal of regression? Number one goal of regression is that we are actually investigating how predictors are associated with the response. Okay, so we want to see how some variables can actually explain the variation in another variable that we called response. That's exactly what we're doing. Okay, and another thing that we actually want to do is we want to assess the effect of one or at most a few predictors on a response. Some of you can, the difference between goal number one and goal number two, before you can actually talk about measuring effect, you need to first measure whether there's a relationship at all. Okay, and that is why goal number one is actually talking about whether a relationship exists. Relationship is the same thing as association. Okay, and the last goal, if a relationship exists and if we're able to measure the effect of predictors on the response, then we can actually use our model to predict. Okay, so the prediction of future values of a response variable given predictors can actually be made. Okay, so why do we want to predict? Because we are in a world where different things happens in different days, and we are so curious about what is actually going to happen in when I have the set of variables, when the predictor assumes this value, what am I going to have? Okay, so because we know different predictor values actually give a different response value. Okay, so I'm actually going to start by example. We have been working on rate my professor data set. Okay, so in a way to investigate relationship between predictors and the response. Okay, of course we can actually study how does a professor clarity score associate with a quality score. Okay, so we actually want to see relationship between that. Okay, how we can actually link the clarity of a professor with a quality. Okay, and that's exactly what we've been doing. Now, under assessing the effect of one, when you want to assess now, an example could be studying which genes are causing the cancer. Okay, this is like giving you some of you topics you can work on in your project. For those of you, that are working on the practical, when you're going to be working on the practical assignment, there's a lot of topics that are available for grab. Okay, now you can be looking at the effect of certain genes. Okay, you know, on cancer. Okay, I can also study how production size affect production time. Okay, you remember the other time where I think I used the example where we're trying to look at, okay, if we have a production company, okay, and if it takes different size, if it takes a different time to run a different size, okay, we can actually collect a data set, a bivariate data set based on production time and production size, and we can actually study the relationship between them. Okay, and in the prediction, of course, if we're able to investigate the relationship between clarity of a professor and quality score, then we can actually predict professor's quality score based on the clarity. Okay, and this is the goal of regression. Okay, now we ask ourselves this particular question. Okay, the question that we are actually asking right now is how does the partial F test do model selection? I told you the other time that one of the two in the model selection is a partial F test. Okay, and I'm actually going to show you the limitation. I mean, what the partial F test does in model selection and the limitation of that. Okay, let me quickly remind you that the partial F test actually compare between simple model and complicated model. I told you before, right? Because when I talk about simple model, at least I must have one regressor. Okay, this is more than uh, one regressor. So here, at least I must have more than one predictor. That's what I want to say. Okay, at least I must. So this one we have one predictor, and this one we have more than one predictor. Does that make sense now? Okay, so of course we use an F test to do model selection there. Okay, partial F test. And don't forget, I put a condition. I said the simple model should be nested within the complicated model before I can use a partial F test. Okay, the simple model have to be nested, okay, within the complicated model. Okay, and you know what? There should be a kind of a connection between the two in such a way that I can actually go from complicated model, I can go to the simple model, okay, when the value of a parameter in the complicated model is 0. Okay, so model selection depends on the answer of, does the complicated model fit the data significantly better than the simple model? And that is a question we actually want to ask ourselves, okay, when we are trying to compare two models. Okay, because we are actually looking for the model that will fit our data set significantly better. Now, let me tell you this. We are in a world where if we actually want to understand the situation around us, we need to collect data set. We believe that we got information in the data set, that need to be reviewed. And that is the reason why the data set actually need to be analyzed, to be able to get the information that is hidden. Okay, but let me tell you this: to be able to extract the largest amount of information in the data set, and that actually depends on the model you are using. Okay, and that is the reason why we are actually comparing. At times we compare at least two models in a way to be able to look for the one that significantly, fits the data, okay, better. Okay, so So the decision is either yes, choose the complicated model, and no, choose the simple model. So your decision is actually going to be mutually exclusive. Mutually exclusive in the sense that when you choose a complicated model, then you are trying to say you are not going to choose a simple model. And in a situation where you choose the simple model, then you're actually telling the world, then uh, the complicated model is not better. Okay. Now, the next thing that we actually want to talk about now is model fitness and model complexity. Okay. Because let me tell you something. In a situation where we are trying to look for fitness, we may be we may be tempted to add more regressors. Okay, and when you add more regressors, that could lead to what I call model complexity. Okay, now the fact remains: does model complexity implies model fitness? Um, at times, the answer could be yes, and at times it could be no. Okay, it depends on the result that we have in the comparison of the uh, simple and the complicated models. Okay, so we actually want a model that fit the data well. Okay, and the model should be relatively simple. I'm going to tell you again. We actually want a model that will fit the data well, but we don't actually want a complex model. Okay, but at times we don't have a choice. Okay, but we want to do it in a way that at the end of the day, what we're going to settle with uh, uh, should be a model that fit the data well and should be relatively simple. Okay, now what are the measures of fitness, of model fitness? Uh, the fact remains that the measures of model fitness is the residual sum squared or the R squared. Of course, the R squared means coefficient of determination. Okay, R squared measures how much percentage variation in the response the model was able to explain. Okay, of course, the model with the with the higher value of R squared, we have a smaller value of the residual sum squared. Okay, so these are the yardstick. Okay, to be able to know whether a model fits good. Okay, so and look at this question right here. Dash, are you going to use a smaller or larger RSS means the model fit the sample data better? So definitely, of course, you're going to be choosing a smaller RSS, okay? Because the model with a smaller RSS is good. It means the residual sum of squared has to be very, very small. And the residual sum of squared is the unexplained variation that we talk about, okay? And you know what? Dash R squared means the model fit the sample data better. That should be larger, okay? That should be larger, okay? So here it's going to be smaller for RSS and it's going to be larger for the R squared, okay? So K, the number of regressors, okay? And the exception for categorical variables, measures model complexity. So of course, let me tell you this. If the number of regressors in the model is so huge, of course, uh, the model would be more complex. Okay, so which means the complexity of a model actually depends on the number of regressors in that model, because the number of regressors will actually implies you got so many parameters to be estimated. Okay, and a smaller k means the model is simpler. Okay, so we want a situation whereby we actually want to have smaller number of regressors compared to the larger number of regressors, and at the same time, we are looking within that framework, to be able to have the best model. Because why is it that we don't want so many regressors in our model we could have what we call the problem of over-parameterization, okay? That could be problem of over-parameterization, okay? When you have so many parameters in a model, can also be a problem, okay? I need you, give me 1 second. I just want to use the bathroom. Thank you. Okay, so I'm back again. Can you guys hear me?
Yes.
Okay, thank you. So somebody asks in the question that so we do not count categorical regressors at all. Of course, you actually going to count the categorical regressor. But let me tell you something. The categorical regressors, uh, you are not going to count the levels. You're just going to count that as one. You know, the regressor for that is one. Because some of you may be thinking that, okay, because the categorical regressor are 2 levels, then the number of regressors is going to be 2 for that. No, that's what I'm trying to say. Okay, for any categorical regressor, for any categorical variable, it's actually going to have 1 regressor. Okay, that's what I meant. Okay, so now, like I said, all regressors related to the same categorical variable will be counted only once. Okay, I think I've answered that question now. Will be counted only once. In other words, these dummy variables added or removed together. Okay, now I want to show you a graph, 2 graphs, and I want you to comment. We want to see how the 3 graph is going to look like. Now, take a look at the graph right here. This here, I'm fitting simple linear regression model. You know, I got 2 regressors with 1 predictor. Okay. Now, this is an example of a simple model. Okay. But take a look at this guy here. This is more or less like an intercept model. Okay. And take a look at this guy here. This is a polynomial regression of degree 4. Okay. I got 5 regressors. Okay, but let me tell you something. This is a special form of a multiple linear regression model. I still have the same variable, only that is being transformed. Okay, now we have fitted this to the same data set. Okay, let's take a look at this. The ROSS here is 0.403. And of course, the number of regressors is 2. K equal to 2. The number of regressors, 1, 2. Okay. Here, the number of regressors equal to 1. Look at the ROSA. The residual sum of square is 4.99. Is even higher than this guy. And you know what? This is a perfect fit. Okay. But you know what? We don't want something like this because we know a model can never be perfect. Okay. So this is relatively what we need, because we live in an approximate world. Okay, and when we live in since we live in an approximate world, okay, we can never perfectly, you know, model reality. Okay, and that is the reason why we're looking for relatively, you know, good fits. We're not looking for the perfect fit. Okay, we're not looking for the perfect because we know a model can never be perfect. Okay, so what I'm trying to showcase right here is just for you to be able to see a relatively good fit model. Okay, now I still on the model fitness versus model complexity. Okay, you take a look at this. I got 2 regressors right here. I got 3 regressors on this one. I got 4 regressors right here, and I got 5 regressors right here. Okay. Now, what am I fitting? I'm trying, you remember the other time when we fitted, when we try to look at the effect of experience for professional workers on the salary. Okay. So take a look at that. Of course, it's going to be a curve. Of course, we know that simple linear regression is not going to be good enough for the data. Okay. This is not going to be good enough because you can see a curve, right? Can see that curve? This is bad. Okay. But if you look at the quadratic, this is like a polynomial of degree 2, which is a quadratic. Okay. This is more or less, this is fine. This is fine. This is going to perfection. But you know what? I would prefer to settle for this. Okay. But because this is relatively simple. Okay. This is very close to perfection. Okay. This is though this is the best of it. Okay. This is the best. Okay. But I can still settle for this, or I'm not going to settle for. Let me tell you something. The only condition under which I'm not going to settle for a model, if that model is is giving us a perfect result, we are not going to. We don't like it. Okay, we don't want. We know no model can be perfect. Okay, so from what I'm seeing here, of course, this model is still good. It's good because it's not perfect. And how am I going to know whether it's perfect? I can actually look at the R squared. The R square of a perfect model is going to be 1. Okay? And we don't want a situation whereby the R square is going to be 1. We want a situation whereby the R square will be close to 1, not equal to 1. So I'm going to show you the R square now. Look at the R square of this one. When I add another regressor, look at the R square is increasing. Can you see that now? Now take a look at the 2. Okay? If you take a look at the 2, look at the R square here is 0.9257. The R square here is also 0.9257. Do you know that if I don't look at the R squared, if I want to look at the RSX, okay, I'm actually going to consider this guy here. But you know what? There is a slight difference between this guy and this guy. Look at that, 1096.384, 1096.377. Okay, I know that this is smaller than this, but this is still fine. You know why? Because this one we have a fewer parameters than this. Okay, look at the number of parameters. The number of parameters here, the number of regressors here is 4, but here is 5. I can still manage this guy here. Okay, in fact, some researchers can manage this guy as well, because they're going to say, okay, this is more or less 92% okay. Okay, so the situation is actually good from here. Okay, so, but if you want to really look at the R squared now, of course, you can settle between this and this. So like I said, I'm actually going to choose this guy because they have the same R squared. Okay, they get the same R squared, though the RSS is slightly different, but because of the overparameterization, I'm actually going to settle for this. And in some situations, some researchers can also settle for this because they're going to argue with you that this is more or less 92% fine. Okay. So that was why I said, how did the RSA change when we add more polynomial regressor? Of course, you can see right here. When you add more polynomial regressors, it's going to be changing. Can you see that now? Okay. And how did R squared change when we add more polynomial regressor? You can see that R squared, but it's going to get to a point that R squared is going to give you the same number. When it gives you the same number, when you add more parameter, it means it has converged. Okay, it means it has converged. Okay. Now, I'm going to take you to the criteria for model selection. Before coming here, I think I've already told you about how partial F-test can be used to decide. We use that as a criteria in model selection, only that you actually need to be comparing two nested model, one simple model and the other one complicated model. And I've also shown you how R squared and the residual sum of square can also be used. Okay, so what we want to talk about here is that, okay, well, the criteria need to consider both model fitness and model complexity. Okay, so when you are trying to figure, if you are trying to figure out the best model, you don't just basically look at the R square alone. You don't look at the ROSS alone, but you also look at the parameter, the number of regressors, because we are actually looking for a relatively smaller model, a simpler model. Okay, so like I said, you should, in the model selection, okay, you should need to consider both model fitness and model complexity. Okay, in model selection, always consider both model fitness and model complexity. Okay, if you only consider model fitness alone and you don't talk about model complexity, okay, that could be, you could encounter problem of computation. You could encounter problem of over parameterization. Okay, and if there's a over parameterization means you get a lot of parameters, and when you have a lot of parameters in the model, there is possibility that the variables will be correlating. I'm going to say that again. There is possibility the variables, the predictors may be correlating. And when variables are correlating, when predictors are correlating, and that could lead to a problem we call a problem of multicollinearity. Okay, it could lead to problem of multicollinearity. Okay, so, and that is the reason why when you are trying to use criteria, or the criteria in model selection, you actually need to consider both the model fitness and model complexity. Okay, so I'm going to introduce entirely new criteria. Number one, I'm going to introduce what we call the adjusted R squared. Okay, why do I need to adjust for my R squared? And I'm going to take you back. When you try to add new regressor into a model, okay, of course, you expect the R square to be increasing. The R square is going to be increasing even if the variable you have added does not have any significant impact. Okay, even if the variable you have added, is a nuisance one. Okay, I'm very sorry to use that word. Okay, so, and that is the reason why we may not be able to rely on the R square, because the R square is highly sensitive to the addition of variables into a model. And that is the reason why we actually need to adjust for our R squared. Okay, and that is why we're going to be using the adjusted R squared. Then another criteria that we also want to use is what we call Akaike information criterion. Okay, Akaike information criterion was was developed by Otorogo Akaike. Okay, and it is called the AIC, and this is actually based. This is one of uh, the 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 the, the 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 most popular criteria used in deciding between models. Okay, so, and we also have another criteria that we call Bayesian information criterion. Okay, so these are the criteria we use in in model selection. Okay, you know what? I can actually ask a question like this. Recall that I call K the number of regressors, except that, when you are talking about categorical variables, you have to count that once. Okay, I think I mentioned that before. Okay, let me ask you this question before I ask. Uh, Give me 1 second. Okay. Uh, okay. Now, SST means sum of square total. Okay, which is the total variation. Now, if you increase your number of regressor, I need someone to answer this question now for extra credit. If you increase the number of regressors in a model, okay, what will happen to the sum of square total? What will happen to the total variation? Is it going to be increasing, decreasing, or not changing? Can somebody tell? Okay, I got a chart right now. Let me read my chart. Uh, Give me 1 second. I'm trying to read my charts, but it's not coming up. Okay. Okay. Yeah. I think a good number of you guys said not changing. Okay. I think I'm going to keep track of that. A good number of you said not changing. You are very, very correct. Oh, my students are excellent. Good job. You guys are so fantastic. Good job. Let me tell you the reason why it's not going to change. The reason why it's going to change because you are talking about response. Okay. So you are talking about response, and you are not looking at that in relation to predictor. Okay. So whether you increase the uh the number of regressor, the sum of square total is actually going to remain the same. Okay. And you know what? The sample size, this is like the degree of freedom for sample size. Okay, I'm only increasing the number of regressors. I'm not increasing my sample size. It's still going to be not changing. But you know what? The ROSS is actually going to be changing. Okay, so the residual sum of squared is actually going to be changing. And of course, the n minus k is also going to be changing. Okay, because k is changing, the n minus k is going to be changing. Okay, please watch out for a question like this in a multiple choice. Okay, there's a lot of questions that can be asked in the multiple choice. Okay, so the question now is, since we know that the residual sum of square is actually going to be changing, and we know that n minus k is also going to be changing when the number of regressors is increasing, okay, then what is the formula that we're going to use in adjusting our R squared? Okay, this is the formula right here. Okay, so what you just need to do, you need to recompute this formula. Though I can ask you to recompute this formula, I can need to compute this. And at the same time, when you run a linear regression using software, whether R, Python, or whatever, you're actually going to have adjusted R square computed as part of the output. But you know what? How do you compute R squared manually? If you want to compute R squared manually, of course, you need the value of residual sum squared, and you need sum squared total, okay? And you need the number of observation, and you need the number of regressors, okay? So this is the formula right here. Okay, so the rule of thumb, select the model with the largest adjusted R squared, okay? So when you have so many models that you actually want to compare, okay, like the same way I'm comparing this one here. As I'm comparing this, I'm not going to base my decision on the R squared, okay. I will need to recompute the adjusted R squared, okay, and the model that I'm going to choose at the end of the day would be the one with the largest adjusted R squared, okay. So that is the rule of thumb. Okay, so that is using the adjusted R squared. There's another criteria that we call a Cockade information criterion. Okay, the Cockade information criterion, we need to compute the Cockade information criterion for the competing models. Okay, and the model with the smallest, I'm going to say that again, the model with the smallest Cockade information criterion is the best model. Okay, so if the acronym that we use for Cockade information criterion is AIC. You remember in homework 4, well, the question that I asked in problem 4 of homework 4, though I've already excused you on that question because on that problem, because you haven't done AIC. Okay, now we're doing AIC right now. Okay, this is AIC. This is called Akaike Information Criterion. It's one of the model selection criterion, and it's in fact is common, throughout the world. It's popular. Okay, so how do I compute my AIC? If I ask you to compute AIC, manually, this is the formula you're gonna use. Okay, you actually gonna, the ROSS is the residual sum squared, and N here is the number of observation, and K here is the number of regressors. Okay, so I want to tell you what is the job of of the AIC. The AIC will penalize, when you have so many parameters, because the AIC is a function on the number of parameters. K here is the number of regressors, is the same thing as the number of parameters. Okay, so it means if you have so many parameters in the model, you are likely to have a larger AIC. And you know what? A larger AIC is not good at all. Okay, so the work of AIC is actually to penalize you for overparameterization. But you know what? The work of the adjusted R square, you are adjusting R square here just because when you add more regressors into a model, you're actually going to have, there's possibility that the variable you are adding may not even have any connection to the model, but you know what? The R square could go up. And that is the reason why we need to adjust for that situation. Okay, and that is the work of the adjusted R square. But for the AIC, it's actually going to penalize one for situation where you have so many parameters. Okay, so like I said, so the smallest AIC, a model with the smallest AIC, is actually going to be the best model. Okay, and of course you now know how to figure out the AIC. Okay, you know how to find the AIC of a model. Okay, you need to have three things. Number one, you need to know the number of observation, you need to know the number of regressors, which is K, and you actually need to know the residual sum squared. Okay, so as you increase K, as the predictor increases, of course, you expect the ROSS, okay, to be decreasing. And what will happen to 2K? Of course, 2K is going to be, it's like you're talking about the multiples of, so it means it's going to be increasing. Okay, so just check about that. It look like I have a chart. I'm going to look at my chart right now. Okay. Uh, Somebody said in the AIC formula, is that n star log or natural log or never? Oh, okay. He said I just answered the question. Okay. Oh, okay. Uh, can you guys see my slide right now? Can you see what I'm projecting right now on the AIC? Can you see that?
Yes.
Yes.
Okay, thank you so much. Thank you. Okay, so so like I said, watch out for that. Okay, so the rule of thumb is that, of course, the model with the lowest AIC is actually going to be the best model. Okay, and you know what? If you are working on, if you're using R software, how do you extract your AIC? Okay, you just write this, extract AIC, and whatever you use to save your model, okay, there is actually going to give you your AIC. Okay, now let me tell you something. When you run a linear regression model, AIC will not be part of your results. But you know what? When you are done, you can actually write this code. Okay, extract AIC. Okay, into whatever you use to save your model. Of course, you're actually going to have your AIC value. Okay, so it means if you have competing models, okay, it means you can get the AIC of all the models, and the model with the lowest AIC is the best model. So another model selection criteria that is also popular is what we call Bayesian information criterion that we call BIC. Okay, so this is also nice. Okay, and what is the formula? Okay, this is the formula right here. Okay, you are still going to use the combination of the sample size, the residual sum of squared, and the number of predictors. Only that right here you need to do, in the case of AIC, what we have here was 2K. Okay, let me show you. You can see that now was 2K. Okay, but look at what we have right now. The difference between them is just this side. They still have the same thing here. Okay, if you go back and see what I have, it's still the same thing right here, but here is 2K, but right here it's actually going to be log of n. Okay, so then the first still remain that, of course, as the number of regressors is increasing, of course, you can take decision regarding the residual sum of squared, and you can actually take decision regarding the log of this multiplied by k. Okay, you can take decision on that. Okay, and you know what? You can also do extract. Okay, you can extract that. Okay, if you want to extract for BIC, you can write extract AIC, but only that you're actually going to specify where k equal to log n. Okay, where k equal to log n. Okay, so this is how you can extract your BIC, and the fact remain that model with the lowest BIC is the best model. Okay, but let me tell you something. If you are trying to work on model, if I were you, I would advise that you use the three criteria. Okay, what decision will you take when or based on the adjusted R squared? Okay, what decision will you take based on the IIC, and what decision will you take based on the BIC? Okay, so in a situation where you take your decision based on these three criterion, of course, you can actually convince, you can actually tell the world that, okay, what I'm working on right now, this model is the best model. It's the best model among the competing model because it has the largest adjusted R squared, it has the lowest AIC, it has the lowest BIC. Okay. Now, the question now is this. Can we have a way to compare different criteria? Is it possible that there's a conflicting interest between the model selection criteria? Let me tell you something. In a time we could have that kind of situation where they don't agree, and the question right here is, okay, if they don't actually agree, so what are we going to do? In a situation whereby the AIC is conflicting with the BIC, or the AIC is conflicting with the adjusted R squared. This is what I'm trying to say. If I have three models, okay, model A, B, and C, okay, if the adjusted R square of model A is the largest, okay, if the adjusted R square of model A is the largest, we expect the BIC and the AIC of such model to be the lowest. Okay, when the adjusted R squared of model A is the largest, we actually expect the AIC and the BIC to be lowest. But we could have a situation whereby a model could have very high adjusted R square compared to other models, but the AIC or the BIC may be larger. Okay, so what can we do in that situation? But what I want to walk you through right now, I actually want to walk you to see, let us compare the criteria. Okay, it's just like we are comparing courts, court of law. Okay, we have seen situation where in the past where a particular court take a decision on something and another court take a different decision. Okay, now the question is, how do we know which court is saying the truth? And somebody may say, okay, why can't we go to Supreme Court? Okay, I know that is what somebody is going to say. That is the the apex, okay? Do we also have Supreme Court? Or do we also have which criteria is supreme? Okay, when there's a conflicting interest among the model selection criteria. Okay, so but you know what? Before we go into which of them is supreme, we actually need to look at whether we need to compare them. Okay, now, to compare them right now, we actually want to use the data set that we used before, where we're trying to look at the effect of the experience on the salary of workers. Okay, whether you are working for Amazon, you're working for Walmart, working for Target, working for whatever company, and we actually want to look at the relationship between your experience in the job and the salary that you are getting at the end of the day. Okay, now take a look at what I have right here. The first model here is a simple linear regression model where the y here is salary and x is experience. Okay, and what I have here is a quadratic. Okay, where the number of, if you look at the number of regressors right here is 2, the number of regressors here is 3. The number of regressors here is 4. And the number of regressors right here is 5. Okay. Now look at the AIC. Okay. And this is their corresponding BIC. And these are the corresponding adjusted R squared. Now let's take a look at that. What is the model? We said the model with the largest adjusted R squared is the best model, right? Okay. So take a look at this. The model with the largest adjusted R squared right here is 0.9241. Okay, and let me tell you something. I showed you something like this before, right? Let me show you. I'm going to show you something now. I showed you something like that before when we try. Oh, okay. Take a look at that. This is it. Okay. The other time I told you that we should settle for this, right? I told you that we should settle for this. But you know what? If you look at the R square here is more or less the same. Okay. But you know what? Because of the fact that we are adding more regressor, I told you we may not be able to rely on the R squared, and that need to be adjusted, right? Okay. So what was computed, we're still using the same data set. Okay. It means the formula right here, it means the formula right here has already been used to compute for the adjusted R squared. Okay. And the formula right here has actually been used to compute the AIC, and the formula right here has actually been used to compute the BIC. Okay. Now, based on that, this is what we now have. Okay. Now, based on the adjusted R squared value, okay, uh, the model with the largest adjusted R squared is this, which is this model here, the cubic. Okay. Can you guys give me 1 minute? I want to use the bathroom. Okay, thanks for that. Are you guys hearing me?
Yes.
Yes.
Okay, so like I said, the model with the largest adjusted R squared is the polynomial of degree 3. Now, let us now check on the BIC. Okay, so what is the model with the lowest BIC? Of course, look at that. The model with the lowest BIC is polynomial of degree 2. Okay, now what is the model with the lowest AIC? The model with the lowest AIC is this. Okay, Now you can see there's a kind of conflict. There's an agreement between the AIC and BIC, okay? Because the AIC and the BIC actually pointed to the second model, the model right here, but the adjusted R squared actually pointed, let me see, yeah, this is greater, 0.9241 is greater than 0.9236. Okay, so the adjusted R squared actually pointed in a different direction, okay? The adjusted R squared is actually in favor of this particular model, okay? While the AIC and BIC actually settle in favor of the second model, okay? So now the question now is, which one are we actually going to agree upon, okay? And that was why I said often this criteria identify different models as the best model. You can see the model identified by adjusted R squared is the polynomial of degree 3, okay, the one with the 4 regressors, okay, based on the fact that the value that I have here is actually the largest, okay? And then based on the AIC and the BIC, okay, the model with the smallest AIC and the BIC is the second model, okay? As you can see right here, different criteria actually identify different model as the best. Okay, now this is just the summary of what we've done before, okay? And then, but let me tell you something. In a situation whereby there's a conflict of interest like this, okay, we normally want to go with the AIC and the BIC. Okay, the AIC and the BIC are more powerful than the adjusted R squared. And when you take a look at the what is it called? When you take a look at the two, they are more or less very close. Okay, they are more or less very, very close. In fact, to 2 decimal is actually going to be 0.92. Look at that. Okay, so and that is the reason why we're actually going to, you know, settle with the model identified as the best by the AIC and the BIC. Okay, so these are the, like I said, these are the model selection criteria that we can use. Okay, so now before I move to the selection method, okay, because there's a difference between the criteria for model selection and selection method, okay? Is there anyone who need clarification? Is there anyone, before I move on? Is there anyone who need clarification? Are you guys hearing me?
Yes.
Okay, so is there anyone who need clarification on the criteria of model selection before I move to the selection method? Okay, I think silence implies that you guys are good. I'm actually going to go to the selection method right now. There's a difference between criteria that we're using in the model selection and the method of selection, okay? The method of selection here can be divided into two, okay? We got what we call the up subset selection, and we got what we call the stepwise selection, okay? I'm actually going to walk you through this method one by one. And let me tell you this, in the selection method that we're actually going to be using, we're still going to be using the criteria along with that, okay? The selection method we're actually going to be using, we're actually going to be using the criteria, the criteria for model selection along with that, okay? And I'm actually going to walk you through that right now. So like I said, we got two selection method, the all subset selection and the stepwise. Okay, I'm actually going to start with the all subset selection right now. Okay. Now, in the all subset selection, considering every model within the scope, when you say all subsets, okay, for those of you who have done mathematics before, okay, you got a set. A set is a selection of distinct objects, okay? And you know what? Within set, we can have a subset, okay? And there's something that we call the power of a set, okay? The power of a set just means the possible number of subsets we can actually have in that set, okay? So we're also going to have all subsets of selection, okay? And I'm actually going to show you right now. Okay, suppose that we're working on two models. Okay, one is a complicated model and the other one is more or less like a simple model. Of course, the simple model here is an interset model, okay? Because there's no predictor right here, okay? There's no predictor, okay? This is an interset model. But here we got 3 predictors, okay? So right here we got 4 regressors, but here we got 1 regressor, okay? Now, if I have something like this, the question is that how many potential models can we actually have within the scope that we're talking about right now? How many? Because we need to consider the possibilities, okay, of of the subset. This is like having a set, okay? Now, how many potential models, okay, am I likely to have? Okay, and let me tell you this. For those of you who have done, okay, let me ask you this question. Have you guys heard about power of a set before? Power of a set. For those of you who have taken mathematics before, have you guys heard about power of a test? Can you guys hear me?
Yes.
Okay, so has anyone heard about power of a test? Like what I mean by that, okay, have you guys done anything that has to do with set theory? Okay, let me do this. I'm actually going to share something with you right now. I'm going to share my dashboard. Let me stop this one. I'm actually going to, okay, so I'm going to share my dashboard. Can you guys see my whiteboard right now?
Yes.
Okay, so take a look at, there's something that we call set theory. Okay, there's something that we call set theory. Okay, now the question I'm asking us right now, for instance, you get a set A, maybe a set A equal 1, 2, 3. Okay, let's say that is a set A. Okay, and they can ask you, just to refresh what you've done in mathematics, they're going to ask you what is the power of a test. Okay, what is the power of a test? Okay, I remember you did this in your 12th grade in the high school. Okay, I'm just trying to refresh that with you, just for you to be able to understand what I'm teaching right now. Okay, so if you are given a set of this, okay, and they ask you what is the power of a test. Okay, so if I want to have the power of a test right here, is actually going to be number 1. I'm actually going to have, as part of the power of it, I'm going to have empty. I'm going to have, let me see, how can I write that? Let me see, empty. Let me see whether I can get a sign on my keyboard. Okay, so let me just write. Okay, before I'm going to write empty, I'm going to write 1, 2, 3. And I'm going to write situation where they appear in 2. Okay, I'm going to write situation where, in 2s like that. I'm going to write 2, 3. Can you see that now? Then I'm going to write 1, 2, 3. Okay, then I'm going to write empty. Take a look at that. This is what we call power of it. So when we are giving this set, the power of this test, of this set, okay, the power of a set. Oh, sorry. I wanted to say set, not test. Set. Okay. So the power of this set is going to be, let's count, 1, 2, 3, 4, 5, 6, 7, 8. Okay. I'm going to count that again. 1, 2, 3, 4, 5, 6, 7, 8. Okay. I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. Now, there's something I want you to see right now. The mathematical formula that they normally give is just the number of sets, the cardinality. There's something that we call cardinality or cardinality. Cardinality, okay? The cardinality, you know, when you look at the cardinality of a set, okay? The cardinality is just the number of elements you have in that set. Okay, let me for do this. There's something I'm going to do right now. What is cardinality? Okay, cardinality of a set. Okay, the cardinality of a set is in here. How many elements do I have? I got 3, right? Okay, so that is the cardinality of a set. Okay, so now if this is the cardinality of a set, if I want to talk about the number of possible subsets that I'm actually going to have, I can have, I can have them in ones, I can have them in pairs, I can have them, as, in threes, like 1, 2, 3, that I can have there. I'm going to have an empty set. Okay, if I want to count, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, I think you can see that now. Okay, and that's exactly what I'm trying to say about the power of a set. So it's more or less that I got this is if I have 3 regressors. Now let me now extend this to what I want to explain. If I have 3 regressors, okay, what's the regressor 1, 2, and 3? The possible number of models that I'm actually going to have is this. Instead that I have a model with one predictor, okay, or I have model with 2 predictors, I have model with 3 predictors, or I have an intercept model. Okay, that's exactly what I'm trying to say. Okay, so let me read my chart. Oh yes, I'm talking about the power set. Yeah, I think somebody corrected me. Initially I was saying test. Okay, so I think I was referring to power set. I think I've corrected that. Thank you for that. Okay, so I'm actually going to go back to what I'm explaining right now. Okay, now take a look at it. This guy right here is a subset of the entire model. This guy is a subset of this. Okay, this can be found inside here. Okay, so this is a subset of that. Okay, and you know what? What I have here is a situation where I'm going to have a subset of one predictor, and they're going to be 3 of that. Okay, they're going to be 3 of that. Look at that. 1, 2, 3. Okay, then another one that I'm actually going to have right now is going to be when I have the 2 together. Okay, the other time I said 1, 2, 3, right? This is the empty that I talk about. Empty. Okay, this is the empty that I talk about. Is empty because there's no predictor right here. This is a situation where I got 1 separately, 2 separately, 3 separately. This is a situation where I got 1 and 2, 1 and 3, 2 and 3. Okay, how many models do I have now? 1, 2, 3, 4, 5, 6, 7. Okay, now you're going to see the last one, and I'm going to have this. Okay, how many models do we have right now? We got 8 models in all. We got 8 models in all. Okay, we got 8 models in all. Okay, Is there anyone who want to ask question? So it means if I in a situation where I'm comparing between this and this, the possible, the all subsets, okay, that we can have, you know, all subset of models that we can have, they're going to be 8 of that, okay? They're going to be 8 of that, okay? So that's what we call the up subset. You consider all the possible models, okay? You consider all the possible models, okay? Do you understand that now? And that's exactly what you're going to have, okay? Now, when you take a look at that right now, so these are the models that we're actually going to consider. So that was what I said in general, where we have k terms in the full model. How many potential models do we need to consider to find the best model? Okay, so how many potential models do we need to consider? So what I'm telling you right now, our k here equal to 4. Okay, our k here equal to 4. Okay, when k, you know, what do I mean by k equal to 4? The number of regressors, okay, 1, 2, 3, 4. The number of regressors equal to 4. Now, if I have 4 number of regressors in a model, what is the possible number of models do I need to consider before I can get the best model? So what I'm telling you right now is that I need to consider 1, 2, 3, 4, 5, 6, 7, 8. Okay, so among these 8 models is where I'm actually going to get the best model. Okay, so strength, very thorough, goes through every possible model within the scope. Okay, we're actually going to derive our strength for that from that by going through the every model within the scope. Okay, then weakness. The weakness we're going to have is computationally expensive when k is large. Okay, when k is large, when the number of predators is large, it's going to be computationally expensive. Okay, so I wanted to see something right here. This is actually showing the charts, okay, between the number of models we can actually consider when you are given the number of regressors, okay, given with the number of, so you can actually, so the relationship between the number of regressors and the number of models, okay, is actually given through that, okay. And that was why I said the number of models that need to be considered in all subset selection, okay. So that is a relationship. Before I move to stepwise method, so which means what you're going to do, you're going to run a regression on this, you're going to run a regression on each and every of this model, okay? When you run a regression on that, then you're actually going to use the model selection criteria that we did before. You're going to use the model selection that we call the AIC, the BIC, and the adjusted R squared to decide on the best model among the compartment models, you know, among the models within your scope. Does that make sense to everyone now? Okay, so you need to decide on the number of models. I think I've showed you how you can actually do that, okay? I've showed you how you can actually do that. And you know what? The graph right here will actually tell you the number of models you're actually going to, you know, is a relationship between the number of models and the number of predictors, okay? Before I go into another method, is there anyone who need clarification?
Yeah, so K also includes the intersect term as well, the number 1.
Exactly. And that is why we call K is a number of regressors.
So
Okay.
so the number of potential model is 2 to the power of K minus 1.
Uh, Okay, did you say the number of, can you say that again?
Yeah, the number of potential models is 2 to the power of k minus 1, correct?
Okay, did you say p to the power of k minus 1, right? Okay,
Yes.
let's take a look at that. P is the number of predictors. That is 3, right? Okay, now you now say 3 raised to power 4. Is that what you say? You said p raised to power k? Because when you say p raised to power k, that would be a lot.
Yeah, so you said it's, so you count that models 1 plus x1 plus x2 plus x3 as you have k equal 4. So the number of models, but then we are only like varying the, now if it includes the x1 to x3, the intersect term is always there. So I guess the number of potential model is 2 to the power of k minus 1.
Okay. Yeah, raised to power k minus 1. Now let me tell you the formula that we use in mathematics to figure out the power of a test. Okay, if I have 3 in a set, okay, if I have 3 figures in a set, okay, you know, okay, let me use this. You're going to see what I'm talking about now. You have asked a very good question. I think I love that. Now, can you see my whiteboard now?
Yep.
Yes.
Okay, okay. Let us pretend that we got 3 variables. Okay, you know, when I say 3 variables, I mean predictors. Okay, so right here, the number of predictors is 3. Okay, which means the cardinality of a set is going to be 3, right? Okay, if the cardinality of a set equal to 3, if I want to figure out the power of a set, if I want to figure out the power of a set, the power of a set, it is a cardinality of a set raised to power 2, then minus 1. Let me say that again. In mathematics, if I want to get the power of a set, it is a cardinality of a set raised to power of 2 minus 1. Now, if the cardinality of a set here is 3, right? What is 3 raised to power 2? That is 9, right? What is 9 minus 1? 9 minus 1 is 8. Therefore, that's why I have 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense to you now? So which means it's actually going to be the number of predictors, okay? The number of predictors raised to power of 2 minus 1, okay? The number of predictors raised to power of 2 minus 1. Now, and that is going to give you 8. You're going to see what I'm talking about right now. You're going to see what I'm talking about right now. Now, how many predictors do we have here? You don't count regressors. Because when I say regressors, you're actually going to count 1. Okay, I got 4 regressors, but I'm not interested in regressors. It's actually going to be predictors, because the difference between this model and this model is predictors. Okay, 1, 2, 3. Okay, it means the cardinality of that set is going to be 3. Okay, so it's going to be the number of predictors raised to power 2 minus 1. So 3 raised to power 2 is going to be 9. 9 minus 1 is going to be 8. Now, if I want to count that, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense to you now?
Yeah.
Okay, so like I said, to figure out the up possible subset is the same thing as the power of a set. And the power of a set is the cardinality of a set raised to power 2 minus 1. Okay, and that was how we got all these ones right here. And we're going to run all the model. When we run all the model, we're actually going to compare the adjusted R squared of this model. We're going to compare the AIC We will compare the BIC to be able to decide on the best model. Okay, so the last thing today is actually to look at the stepwise approach. Okay, the stepwise approach can be divided into three. We could have a backward, we could have a forward, and we could have both direction. Okay, so I'm going to show you how backward work and how forward work and how both direction work. Okay, so you're going to see the way we're going to do that right now. Now I want to explain backward now. You're going to see how backward work, and that backward is called backward elimination. Okay, in the backward elimination, I'm actually going to have all the variables in the model, all the predictors. It's like I'm actually going to use a full model, and I'm actually going to be eliminating them one by one. What am I going to eliminate? I'm actually going to eliminate the insignificant variable. Okay, let me tell you something. When we are using this approach, you can base your criteria on p-value. You can base your criteria on AIC. You can base your criteria on BIC. You can base your criteria on adjusted R squared. Okay, so for the backward elimination, we're going to have a full model. We're actually going to be removing the insignificant, or we're going to be removing the something one by one. Of course, and for full model, we're actually going to be adding. Okay, and we can also add for both direction. But the example that I'm actually going to showcase right here is using AIC. Let me tell you something I told you the other time. The AIC and the BIC, they are the supreme of the model selection criterion. Okay, because you could have a situation where there could be a conflict of interest. And that is the reason why we actually want to rely on the AIC. Okay, so we're going to do a backward elimination with the AIC right now, where we want to use a tree graph to illustrate the process of stepwise method. Okay, so like I said, we're going to start with the AIC. We're going to start with a full model. Okay, because we want to use a backward elimination. We actually want to be eliminating insignificant predictor. Okay, so we're going to start with a full model. Okay, so we actually want to assume that, okay, we have run the full model and this is the AIC. Okay, so in step one, what are we going to do in step one? In step one, now take a look at that. When we run this guy here, okay, and by the time it indicates that X3, okay, maybe it's significant, okay, and when you remove that from the model, of course, and we recompute the AIC, we got the AIC of -110. Okay, you can see in the backward elimination, that is what we do. Okay, so we're going to consider the possibility. Okay, like this is having the model, having all the predictors in the model. Now, what of in a situation where I consider the pair of that, just two predictor, X1 and X2, or I consider X2 and S3, or I consider X1 and S3, okay? And I have the AIC associated with each of that. So in step one, you need to first compute, you need to get the AIC of each of the model, okay? So when you do that, in step two, of course, there are some. Now, if you look at this is the AIC that we have before. Okay. Now, right now, if you take a look at what I have here, the one with the smallest AIC in step one is this guy here. Okay. Of course, -119 is the smallest compared to that. Okay. Can you see that now? So, because let me tell you this, we actually want an improvement on this. We want an improvement on this. Okay, -1.12. This model is bad because the AIC is increasing here. We don't want this one. Okay, but this is fine. This is fine. But the lowest of the AIC is this guy here. Okay, and that is the reason why we said, okay, you know what, instead of considering this, we're going to consider that. It means S2 may likely not to be significant. Okay, because the one with the X2, the model with the S2 has the IAIC. Okay, and that is the reason why we are, this. And we can also have a way to further improve on this. Okay, by trying to consider either X1 as a predictor in a model and X3 as a predictor. Okay, now when you consider this rule right now, okay, which one is an improvement on this? Because this is minus 119. Of course, it's actually going to be this guy. Okay, this is smaller than this. This is bigger than this. Okay, I think you can see that now. So which means, and that is the reason why we are actually interested in this. Okay, and you know what? Somebody may be thinking that, okay, why not also consider a model without predictor? But you know what? The model without predictor will be the worst. Okay, look at that. Compare this with this. Okay, the AIC here. Oh, okay. Sorry, that's fine. This is better than this. But you know what? This is not better than this. Okay, so if you take a look at what we have right now, the one with the smallest AIC is a minus 121. Okay, which is that guy here. Can you see that now? So, and this is the step right here. So this is what we call, what I just explained right now is a backward elimination with the AIC. And so I said, starting from the most complicated model being considered, this is the most complicated model. And at each step, remove the regressor or categorical predictor variable that reduces AIC the most. Then stop the process when AIC stop decreasing. Okay? Stop the process when the AIC stop decreasing. Okay? Now, you're going to see that the AIC has been decreasing all the way to this. But you know what? From here, when you go further to this, it's going to increase. It means you're going to stop the process right here. Okay? It means you're going to stop the process right here. Okay? Now, that is the stepwise, now for the forward, you're going to start from the intercept model and you're going to be going up by adding. Okay? Now, you add the X1, this is you compute the AIC, you add the X2, you compute the AIC, you add the S3, you compute the AIC. Can you see that now? Okay, this is minus 109. Okay, and this is up. Okay, if you look at this one, they are both smaller than this one. Okay, so the next thing that you're going to do, you're going to choose the smallest one. Okay, what is the smallest one right here? Okay, is this guy here. Okay, now when you choose the smallest one, then you're going to be thinking whether you should, right here you have X2. You're going to be thinking whether you should add S3 or you should add X1. Okay, you're going to be thinking whether, since the S2 is okay. Now another thing you're going to think about is, okay, whether you're going to add S3 to that or you're going to add X1 to that. When you do that, your AIC is minus 116 right here, and your AIC is minus 110. Okay, and you can see what happened to the AIC. The AIC go up. Okay, the AIC go up. Okay, and if the AIC go up, it means this is going to be your model. Okay, if your AIC go up. So I'm going to show you the process right now. You can see there is the way. And so the forward is saying that, okay, starting from the simplest model, which is this one, at each step, so add the regressors, and the predictor variable reduces the AIC the most. Stop the process when the AIC stop decreasing. So I'm actually going to stop the process right here because the AIC is now increasing. Okay, but I'm actually going to continue when the AIC is still decreasing. Let me read my chart. Oh, this is 320. Okay, I think I'm actually going to stop here today. Okay, tomorrow I'm going to stop from stepwise before I start the topic for tomorrow. Okay, I'm going to start from stepwise. okay, because the time, my time is already. Oh, let me ask you this question. Is any one of you have lecture now? Do you have other lecture now? Do you want us to finish the stepwise now, because we just have like 4 slides, but this is 322? Or do you want us to finish that, or we should continue tomorrow? I need a response from you.
That doesn't really matter.
Oh, somebody said we can keep going. Okay. I want to know. Oh, somebody said we can finish. Oh, thank you for that. Oh, good job. Okay, we're actually going to finish that. Thank you. Thank you. Oh, you guys are wonderful students, you know. Okay, so we're going to finish that. We're going to finish that. Okay. So now you know the difference between the backward and the forward. Okay. In the backward, you're going to start from the full model. In the forward, you're going to start from the simple model. Okay. Particularly, you're going to start from the intercept model. Okay. So, okay. So, I'm going to, so I think I've explained the forward right now. I mean, the backward, and I explained the forward. Okay. So, so on the forward again, of course, you can actually see that I have to stop right here, because when I attempted to, by the time I made attempt to go, you know, I added x2, s3 to x2, and I added x1 to that. I could put the AIC. The AIC is even bigger than this, and that's why we're actually going to stop here. Okay, that's why we're going to stop right here. So let us now compare uh, the two the two method the two method of selection. Okay, now this model by forward agree with this model. Okay, the predictor is x2. Let's look at the backward. What does he agree on? Okay, the backward agree with the model with x with the model with the predictor x3. Okay, you can see that there's a conflict. Okay, you can see a conflict right now. Okay, we're using the same data set. Okay, the backward elimination and the forward elimination actually agree on different model. I think you can see that now. Now let's now go to the stepwise. Okay. Uh oh, okay, this is another example on the backward. Okay, this is another example on the backward elimination. Okay, you know, in the backward elimination, you know what we normally start with. We start with a full model. Okay, and we made an attempt to have, you know, in twos. You remember where you use the idea of a power set in twos, and when you have them in twos, you compute the AIC. Okay, and we're actually looking for a way to improve on this AIC, because for now this is like this is a better model. This is good until we see a model that have a smaller AIC. Okay, and when you take a look at this in the step one, of course, uh, this is the one, because look at the AIC here is smaller than this one. The AIC here is smaller than this one, so it's between this guy and this guy, but this is better. Okay, this because this is smaller than this. Okay, right here we are on x1 and x3. Okay, we can also consider a situation where we're going to have x1 separately, we're going to have x3 separately. Okay, then we're going to work on the AIC. Okay, so if you look at the compare the AIC here and the AIC here, this is larger than this, and that's why we're not going to consider this, but this is smaller than this. Okay, then we're going to go again. Okay, so since we have a simple predictor, we can go to the intercept model. And you know what? If you look at the AIC here, the AIC has jumped up. Okay, because of that, we're going to say this is the best model. Okay, now the question here: how many models do we consider in this backward elimination process? And don't forget the number of regressors. This is not predictors. K represents regressors. Okay, so K represent regressors. Okay, you can see 1, 2, 3, 4. But the number of of predictors is 3. Okay, and how do you know? 1, 2, 3, 4, 5, 6, 7. Okay, you can see that right now. So we're actually in this particular elimination that was done. Okay, in this particular elimination that was done, the number of models is 7. 1, 2, 3, 4, 5, 6, 7. Now we're going against a general formula right now. You know, the other time, the general formula was the cardinality of a set raised to power 2 minus 1. Okay, you know, the other time we got 8, right? But it depends on your elimination. The elimination here, okay? The number of models that we consider was 1, 2, 3, 4, 5, 6, 7. Before we now decide on the best, okay? And that's exactly what we're trying to talk about, okay? And how many models do we need to consider at most in any backward elimination process with k equal to 4? Okay, now this one said, how many models do we consider in this backward elimination process? In this, how many that we have done is 7. Okay, but here he said, how many models do we need to consider at most in any backward elimination process with k equal to 4? Now this is different from this. Okay, when we say at most, the highest that we can consider, then you're going to make use of that formula that I mentioned the other time. Okay, I know this is basically you're going to use that formula there. Okay, now we miss out the model with the lowest AIC. Okay, and of course that model is the, you know, when you take a look at what I have, okay, the model with the lowest AIC is this one. Okay, but before, you remember that when we did the other time, it was minus 125. Let me take you back. Okay, can you see that here on that forward? You see that now? On that forward, okay? So which means when I do backward, with the backward, I'm actually going to mix out on X2 as a model with the lowest AIC. Okay, so that is one of the disadvantage of that. Okay, so we miss out the model with the lowest AIC. Okay, now okay, this is another example of the forward with the AIC. Okay, so this is showing you another example. I think you can see that now. You started with you know, forward, we start with the smallest model, then you started adding predictor. Okay, can you see that now? Then you look at the AIC. Okay, which one has the lowest AIC? Not just having the lowest AIC, but the AIC has to be smaller than the one you start with. Okay, so all of them are smaller than this one, but this is the lowest of the lowest. Okay, and you know what? When you have this guy here, you're going to be thinking of adding X1 to it and adding X3. Okay, adding X3 to that is this model. Okay, adding X1 to that is this model. Okay, when you compute the AIC, okay, none of this AIC is smaller than this. Therefore, I'm actually going to stop on this. Okay, and I can actually count the number of models to arrive at the best model using the forward selection with the AIC. If I want to count, I'm going to do 1, 2, 3, 4, 5, 6. Can you see that now? Okay. So, and you can also be asked the same question. How many models do we consider in this forward selection process? Of course, you see 1, 2, 3, 4, 5, 6. Okay, you can put your answer there. And how many models do we need to consider at most in any forward selection with k equal to 4? Okay, you can actually answer that question with the curve that I showed you the other time. Okay, now in general, with k potential regressors and or categorical predictor variable, how many potential models do we need to consider at most to find the best model in the backward elimination or forward elimination? So I'm going to walk you through as time goes on. Now, we have looked at the forward, we have looked at the backward, and we realize that, you know, there is possibility that the forward may miss a model with the best AIC, and the backward may miss the model with the best AIC, and that is the reason why we may want to go stepwise. And take a look at this. Two roads diverge in a wood, okay? And I took the one less traveled by, okay? If you take a look at this road right here, and you see the one right here, you're actually going to see that a lot of people actually travel in one part than the other, okay? So I took the one less traveled by, and that has made all the difference, okay? So, you actually want to compare between the, it's like, can we have a way to combine the forward and the backward in the same method? Why do we need to compare? Why do we need to combine the two in the same method? It's just because of the fact that there's a possibility that using forward alone, we're actually going to miss out something. And using backward alone, we're actually going to miss out something. And that is the reason why we're actually going to consider the stepwise, okay? And the stepwise, we're actually going to proceed in both directions, okay? So, of course, the strength here is computationally efficient, and the weakness here is not thorough. In some cases, may miss out the best model, just like what you know. Okay, so I'm going to leave the stepwise approach to the next, to our next meeting. Okay, you can see right here. When we started, we said we're going to have backward, forward, and both direction. Okay, I'm going to leave both direction for our next meeting. But the fact remains that three of them are called the stepwise. Okay, so is there anyone who have any question for me today? Because that is going to be the end of my lecture. Is there anyone who have any question? Let me tell you, looking at looking at the forward and the backward, it's more or less like the journey that we have that I'm showing you right now, because we want to believe there are so many ways to get to our destination. Of course, we are actually looking for the not only faster route to get to our destination, but the route, with the more efficient, and that is the reason why, and that is what we do in model selection criteria. We actually want to get the best model, but when we want to get the best model, we should also consider not only model fitness, we should also consider model complexity. Okay, we should also consider model complexity. And somebody said, when you left the call at the beginning of the class, Zoom put me in charge of the room. I am benevolent and give everyone 10 extra credit points. Can we honor that? I don't really get what you mean. I don't get what you mean by that. I don't get what you mean, because when I left everyone, when there was at the beginning of the class, when I actually when there was a kind of a break in my transmission, I think I have to log everybody in again, and I started all over. Okay, and I started all over. Okay, somebody said, do we still have? Oh, he said it was a joke. Okay, now somebody said, do we still have homework this week? Of course, homework will be uploaded every Monday night. I think I told you that. Okay, you're going to have your homework uploaded every Monday night, and it's actually going to be due every Sunday night. Okay, homework uploaded every Monday night, and it's actually going to be due every Sunday night. Okay, so, and you still have your homework 4 ongoing. Okay, you guys are still working on your homework 4. Okay, so the grader will actually grade homework 3. Okay, and you're actually going to grade homework 4 as soon as you guys have submitted. Okay, so I think I want to thank everyone for attending my lecture today. I'm very sorry for having an extended lecture time because we're supposed to stop by 3:20, but this is 3:37. Very sorry to take your time because we needed to finish this because this is the 5th week of the semester. Okay, so I'm actually going to meet you again tomorrow. Okay, make sure you guys make sure you stay safe and have a good day.
Thank you. Have a good
You're
day.
welcome. You're welcome.